Hey everyone, welcome to part 3 of our online course. Today we'll be covering wall and transfer designs. So transfers occur whenever we need to transfer load from one location to another. So this might be when we want to move a column. So if the architect might have columns running one location through the apartment floors, then as you get to the bottom levels, there might be podium levels, and then we need to move the columns. So we need to transfer the load from one location to another. Another reason would be header beams. So say, for an example, in a core wall, you have your lateral loads pushing on the core, and then we have a doorway going through the wall. So we need to transfer the loads from the top of the core, past where the header beam is and the doorway, and back down to the core and subsequently to the foundations. So what we're going to be showing you is the difference between the strut and tie approach and the deep beam approach, which might have been covered in university, but today we will be giving you an introduction to it. And the importance of panel breakups. So when you have design for precast panels, which is starting to become the trend, they are always limited by the crane capacity or the truck capacity. So the panel, you might design it as one big wall, but the panels will be broken up into certain segments. So the effect of having panel breakups and how to do them effectively. Also, the difference between flexure and tensile reinforcement. So tensile reinforcement is for the strut and tie approach, which we'll cover, and if you design it as a deep beam, the reinforcement's going to be in flexure.
This is the case with most engineering problems. You are best off drawing a section of the area you're trying to design and drawing an elevation. So here we have one column here on one floor transferring to two columns on another floor. So we've got one column here and one column here. So we have to get the load from here to here and to here. So the first thing we're going to talk about is the strut and tie method. So with the strut and tie method, you as the designer get to choose the load path, but usually the simplest option is the best. So right now we could potentially make a real complicated truss system, but you're best off just choosing the simplest. So what we're going to do is say the load starts here. And one important thing as the designer is to choose where the nodes are. So where the nodes are is where you're going to put the reinforcement. So right here, we have the option of keeping the reinforcement inside the beam, inside the wall here, or we can choose the reinforcement to go into the slab. So depending on what's surrounding this area and the amount of reinforcement required, you can make that decision. But for this case, we will put the node here, so it's going to be in the center of the column. So the loads go from here to here, then back through the centroid of the column, and same for this case. So right now we're going to go in the slab. So we're going to make sure we can fit the reinforcement in the slab with the reinforcement that's already meant to be in the slab. And then we take the load from here down to here, down to here, from the centroid. So we've got load going like that. So these are our two struts. So as we're pushing down here, these are in compression. So as we're doing that, we're going to be pulling this out. So our reinforcement is going to be in the slab in tension.
So what we've covered here is putting the node inside the slab zone right above central to the column. So we have a node here and a node here. So if I zoom in this area right now, it's clear that we could easily get the reinforcement way past the center of the node is what we want, because we want full development of the reinforcement here. So development means the length of reinforcement required until the full tensile stress is developed. So in this case, we can get full tension at this point here. But what would happen if from the very start of the design process we move the node inside the precast wall. So in this scenario, it would move it up like that. So now we would have to put our reinforcement inside the wall. So for this, here you can see straight away, it's hard to get the full development length required past the center of the node, as the edge of the wall is in the way. So the full development length is usually 40 times the bar diameter. So that means we need to get 40 times the bar diameter past here. So if these were N20 bars, we need 800 mil from this point back to this point. However, in the case of a wall, if you've got an edge, what we can do is we can cog the bars. So in this case, we put a cog like that, and that means we can get 50% development from the cog half here, and then that means we only need to left to get 50% development past the center of the column. So you can see straight away it's a little bit harder if you put the node inside the precast wall, but at times it's the only choice. So the strut and tie method is best for a lower span to depth ratio. So if we get a higher long span to depth ratio, we can probably start looking at the deep beam method. So there's two ways of solving this problem. One is strut and tie, the other deep beam method. So if you design this as a deep beam, you use the same process as simple beam theory to calculate the maximum bending moment at the centroid, shear forces at the edges. So one way of doing this is using the CEB method, which can be used in most textbooks and covered in university. So the main difference for the strut and tie method and the deep beam method is the tensile or the reinforcement. So for the strut and tie method, the reinforcement is pulling, so that's in tension. And for the deep beam method, it is actually in flexure, so just like a normal beam. So if it's in flexure, the development past the very ends of the column is not as critical as it is for the strut and tie method, because the maximum bending moment will be in the centroid, so the maximum tensile reinforcement required is at the center of the span. So another thing to consider is the lapping of the reinforcement. So reinforcement can only come in certain lengths. So sometimes you need to put two bars together instead of coming in one big bar. So for the case for the strut and tie method, when the reinforcement here is in tension, if we just simply lapse the bars together, something like this, then because this is in tension, this will just pull all the way out and it won't be effective. So what we need to install if reinforcement is in pure tension is something called couplers, mechanical couplers. So mechanical couplers are technology that allows you to screw in two different rebar from either end, and they are assumed to be fully developed and fully connected to form one long bar. As opposed to the strut and tie method, so when the reinforcement is in tension, if you use the deep beam theory, as this is in flexure, you can simply lap the reinforcement at the center of the transfer and it'll be okay because it's in bending and they're not going to get pulled out. So now you've designed the transfer, taking the load from one location to another. So for this case, we're taking from a column through to a floor, down to another two columns, due to probably an architectural constraint or something. Another thing is header beams in cores, which we haven't covered here, but you're sure to cover at some stage in your career. So now it's been designed for, the next important thing to consider is the panel breakup. So this isn't for just transfers, this is for all wall designs and all columns. So you're going to, before you start the design, think about the crane capacity that the builder can get onto the job and think about what can be carried in the truck to site. That's if they're going down the precast route. So right here I've shown a precast panel breakup. So this might have been the crane cannot carry the whole panel. So we had to break it up into two. But remember, we have reinforcement here. So if we design this as a strut and tie method, how are we going to get the bar from here to here? Or similarly, if it was designed to be a deep beam in flexure, how is the reinforcement going to transfer here to here? Are the two panels going to be able to be connected properly? So we're going to understand all the forces that go together to connect the two panels. So one solution we have here is to install or design for a wet joint. So in this case, we have two different precast panels on either side, and due to the crane or truck capacity constraints, we had to break up the panel at this transfer, but we have to also connect the panels together so we know all the load's going to transfer from here back to the columns as we've discussed before. So for a wet joint, what we do is we have the two panels broken up, and then we have the bars lapping here if the bars are in flexure, or if they're in tension, you might have mechanical couplers. And then we just simply pour this part in situ, concrete here. So then after that, we can assume a full connection with a wet joint. So there we have it, guys, part 3, transfers. So that should be a good introduction for you to go off and start your designs and looking through the codes to get you started with the strut and tie approach or the deep beam approach, understanding panel breakups and the difference between flexure and tensile reinforcement, also developing the reinforcement past the node.